Hi everybody, and welcome to part 2 of our thermochemistry notes. All right, in our last set of notes, we saw how you can use specific heat to figure out how much energy it takes just to change the temperature of something. Today we're going to talk about heat and changes of state. So let's get ready to talk about that. Okay, so heat and changes of state. Heat energy is needed to change the state of something. And when we talk about changing the state, we're talking about things like melting and boiling. All right, all things that we're very, very familiar with. All right. However, the gain in heat causes the change of state instead of the temperature change. So what exactly do I mean by that? Well, when temperature changes, that's a change in what we call kinetic energy. And we know that temperature is a measure of the average kinetic energy of something. However, when state changes, when something is melting or when something is freezing or boiling or condensing, the type of energy that is changing is a change in potential energy. All right, so potential energy. And we abbreviate that PE. All right. Now, the interesting thing about potential energy is we can't measure that with a thermometer, all right, because thermometers measure kinetic energy. So that's why when you think about, okay, at what temperature does ice melt? Well, it melts at 0 degrees Celsius. At what temperature does water freeze? Well, it freezes at 0 degrees Celsius. So you have an energy change there, but it's not a temperature change. So we're going to need some new calculations to kind of help us with this. And one of the constants that we are going to be using is what is known as the enthalpy of fusion. The word enthalpy is the same as energy. Just sometimes we use one, sometimes we use the other. No real reason why. But enthalpy of fusion is abbreviated delta H fuse. All right, and that is the heat needed to melt 1 gram of a specific substance at its melting point. For water, and this is one you want to kind of underline because you're going to be using this in your practice sheets, water's enthalpy of fusion is 334 joules per gram. We also have what's known as the enthalpy of vaporization, which is delta H vape. All right, the heat needed to vaporize 1 gram of a specific substance at its boiling point. And we can see here for water, it has a really high enthalpy of vaporization. And any of us who have boiled water before knows this. It takes a long time for water to boil because you need to add a lot of energy to it. Some other constants that you're going to be using in this unit are the specific heat of ice, all right, and the specific heat of water vapor. Please remember, specific heat is specific to the state of matter. So the one we already know is what we call the specific heat of just water, which means that we're talking about liquid water. All right, so I'll put that in parentheses, liquid. And that is 4.18 joules per gram times degrees Celsius. So all of these constants are going to end up being used by us in our next example of a problem that we're going to be doing. So let me introduce you to a type of graph that is called a heating and cooling curve. All right, heating and cooling curves typically are going to look very similar to this, where they have a stair-step kind of a situation going on. The x-axis, you'll see it's the heat added. The y-axis is the temperature. All right, you have these areas where there is an incline, an increase in temperature. You are changing the temperature there. When it plateaus, that means you're changing state. All right, so let's take a look to see what's going on with this type of question. So here we go. How much energy is needed to raise the temperature of 50 grams of ice starting at negative 14 degrees Celsius to water vapor at 125? Well, all right, we're going to go ahead and start and use this graph. And down here, we're going to say we are at negative 14 degrees. All right, so the first thing that's going to happen is that you have to raise the temperature, okay, to the freezing point, which this is for water, and that's 0 degrees Celsius. So that's going to be one problem. Then you still have ice here. Then we're going to melt that ice. So that's going to be our second problem. Now we're going to have liquid water at 0, and we're going to have to bring that liquid water all the way up to the boiling point, which, as we know, for water is 100. So that's going to be a third problem. Then when we're at 100 here, we have to vaporize it. That's a fourth problem. And then our last place we're going to is that 125. And that will be our fifth step of a problem. So there's a lot of steps that go into this, but none of them are really that hard. Let's just take a look and go through these steps together. All right, I'm gonna pull back the sheet here that has the constants because we might be using those. All right, so what we're gonna do is we're gonna start with the ice and raise the temperature to the freezing point. So let's see what this problem is gonna look like. All right, so Q. Okay, so this part of our graph, if I bring our graph back here, this is the number one part. So we're gonna be going from -14 up to 0. So this is a change in temperature, which means we're gonna be using specific heat equation. Remember that we used last time. So that is Q is equal to the mass, all right, times the specific heat times the delta T. That's gonna be our equation anytime we do a change in temp. So for this problem, all right, so my Q, my mass is gonna be the same throughout these problems. So it's 50 grams. The specific heat, remember we're at -14 and going up to 0. So I have to use the specific heat of ice. So that's 2.06, and that's in joules per grams times degrees Celsius. And then my delta T, I'm going from -14 to 0. So that is gonna be 14 degrees Celsius. All right, I'm gonna plug this into my calculator. So 50 times 2.06 times 14 gives us 1442 joules. All right, so that's one problem. Okay, next up on our graph, we're at step 2. Step 2 is our melting the ice. So that's what we have to do. Now this is gonna be a different equation. And for this one, we're gonna go Q is equal to the mass times the enthalpy in this problem of fusion. That's it. Remember, changing state, there is nothing about the temperature, so we don't worry about that. So here we go, Q. We're still dealing with the same sample of water. This 50 grams is not gonna change. Our enthalpy of fusion, if you remember from the notes just a moment ago, enthalpy of fusion for water is 334 joules per gram. 334 joules per gram. And that's it. We're just gonna go ahead and plug that in. So 50 times 334, and that gives us 16,700 joules. All right, fantastic. All right, so now, and I know there's a lot of referring back to these graphs. So now we have melted the ice, so we're right here. I am at liquid water, and I want to bring it from its freezing point at 0 to its boiling point at 100. So we're going to go a change in temp. We're back to a specific heat problem. All right, so Q is going to equal still these 50 grams. Now specific heat of liquid water, which is 4.18. All right, and my delta T, I'm going from 0 to 100. So that's 100 degrees Celsius. Okay, so we're going to give this one a try. So we're going to go 50 times 4.18 times 100, and that gives us 20,900. So 20,900 joules. All right, we're almost there. Okay, we still have 2 more steps to do. Our next step, all right, we have done 1, 2, so check off 1, check off 2, check off 3. We need to vaporize this water. All right, so we need to vaporize this water. So again, I'm going to be using the equation Q is equal to mass this times the delta, enthalpy of, and this should have been a delta H up here. So a delta H of vaporization. So here we go. Q is equal to 50 grams, still the same 50. And remember from our notes before, the enthalpy of vaporization for liquid water is 2260. So 2260 joules per gram. All right, so we're gonna plug that in and we're gonna go 50 times 2260, and that gives us 113,000 joules. A joule, again, is a really tiny unit, so don't be surprised that you do get rather large numbers as your answer. All right, our final step looking at our graph is we have vaporized it. We now have steam, but I don't have steam just at 100. I said I was going to 125. So I'm going to be back to doing a specific heat problem. So Q is equal to 50 grams. The specific heat of water vapor, otherwise known as steam, is 1.7 joules over grams times degrees Celsius. And our change in temp for this one, because if you remember the question said water vapor is ending at 125, we're already at 100. So from going from 100 to 125, our change in temp is 25 degrees. So we're going to plug this in. So 50 times 1.7 times 25 equals 2125 joules. And then the final step in this problem is to add all of these numbers up. All right, so let's go on ahead and do that. And 1442 plus 16700 plus 2900, there we go, plus 113000, and plus 2125, which gives us a total answer of the total amount of energy needed. And I'm going to go ahead and round this a little bit because that's a lot of digits to give me. And I'm going to say it's 154,000 joules, or more likely you would see this as 154 kilojoules. All right, as our final answer. If you leave it with all of the digits, that's totally fine, all right, and that won't be a problem. But don't be surprised if on answer keys and things I do round it. Also, when you're doing your practice with this, please realize that this was as many steps as possible. And by that, I mean we started in the solid state, ended up in the vapor state, both below the freezing point and above the boiling point. I could ask you kind of any chunk of this graph, and it would just be a shorter problem. It would not have all 5 steps, okay? So we'll do lots of practice with this. Have a great day, everybody.